Okay, so friction, there's two main types of friction, kinetic and static. What does the word kinetic mean to you? What should that bring to your mind when you see the word that kinetic? Motion, yeah. So kinetic friction is friction that acts in the direction opposite the velocity, but it happens while the object is already in motion. Okay? So kinetic friction is really looking at an object once it's already in motion. Okay? So we're looking at an object once it's already started to slide. Okay? And that's what we're really looking at here is sliding things, not rolling things. We're looking at things that are sliding. And this kinetic friction is once they are already in motion. So you might want to make an extra note for kinetic friction. This is for objects already in motion. Okay. So the magnitude or the size of our kinetic frictional force depends on the two surfaces that are interacting, right? Whether it's ice, whether it's cement, whether it's rubber, those types of things depend, and they change the amount of friction that we have acting. Okay, so give me some examples of surfaces that have little friction. Ice is one, right? When things are wet, they have less friction. What are things that exert a lot of a frictional force? Can you think of certain surfaces that might exert a big frictional force? Sandpaper, yeah. Carpet. Those types of things, those types of surfaces exert a greater frictional force. So our types of friction here and our magnitude of our frictional forces do depend on the surfaces in which are interacting. Okay? Our kinetic friction and our frictional force has found to be proportional to the normal force. Okay, and I want to demonstrate this here in just a second, but that means it's essentially proportional to the weight of an object, right? When an object is at rest on a table, or when it's moving horizontally only, if it's not moving vertically, that means our normal force and our weight are equal to each other, which means our kinetic friction can be proportional to the weight if there's no vertical acceleration. Okay, so to demonstrate this, I want you to rest your hand lightly on the table, okay, and just start sliding it. Okay, forward or backward. It seems to be more easy to slide it backward, but try and slide it forward, just with pretty little pressure on your hand. Okay? Now I want you to increase the normal force that the table exerts on you. Right? You have to push down with more force. Is it harder to get your hand to slide? Yeah. As you increase the normal force, as you increase the force you apply on the table, which increases the normal force back on you, you increase the frictional force. Okay? These two are directly related, and they're related with this equation right here. Frictional force equals coefficient of kinetic friction, that's what this symbol is right here, and we'll talk about that in just a second, times the normal force. So it's frictional force equals mu times the normal force. So this is a Greek letter called mu, and the subscript K just means kinetic. Okay, so what unit should our frictional force be in? Newtons, right? This is going to be in newtons. Our normal force is in newtons. Our coefficient, this value right here, has no units. Okay, so this coefficient has no units. Okay, it's a value. And we're going to talk about the coefficients here in just a second. So that's our first main type of friction, kinetic friction. Once something is already in motion, this is a frictional force that's exerted. Okay, it's already in motion. This is static friction now, our second type of main friction. And what's it mean for something to be sitting static? Okay, yeah, electricity, but that's not what I'm talking about here. Motion. What's it mean to be static? Still, right? It means to be still. So static friction is the frictional force of an object at rest. Okay, the frictional force that's holding an object in place at rest. Okay, and what does Newton's first law tell us about objects at rest? They want to stay at rest. Objects at rest want to stay at rest. Objects in motion want to stay in motion. So when we're talking about static friction, that means to overcome this rest position, we've got to apply a force that's large enough to overcome this static frictional force, okay? You have to overcome the static frictional force to put an object in motion. So you have to overcome a greater force to put an object in motion than to keep it in motion. So which of these two forces would we expect to be larger, the static frictional force or the kinetic frictional force? Static, right? It takes a greater force to put something in motion than to keep it moving, right? That goes right along with Newton's first law. An object at rest wants to stay at rest. An object in motion wants to stay in motion, okay? So the force that we have to apply to overcome static friction is greater than the force we have to apply to keep an object in motion. Does that make sense? Okay, so here's our equation for static friction, and really it doesn't change at all. This is still a frictional force, so you can still label it F sub little f for friction. We're just talking about the maximum amount of friction force because static friction is going to be the maximum amount of friction that could be applied on an object. Okay, but still you can go ahead and label it F sub f for friction. Our coefficient here has an S subscript for static, and we're still taking it times the normal force. Okay, so the only thing that changes here is our coefficient of static or of kinetic friction. All right, and I want you to read this paragraph on page 127, okay? That whole page 127 talks about these two different types of frictions and the coefficients that go into them. So I want you to read page 127 about these. Okay, so based on what we've talked about so far and based on what you read in that page, which value would you expect to be higher, the coefficient of static friction or the coefficient of kinetic friction? Right? Which of those mu values would you consider should probably be a larger value? Static, right? The coefficient of static friction. Those two surfaces are going to exert a greater force. So what I want you to do is turn to page 129. Okay, page 129 has a chart with these values of coefficients of friction. And essentially what the coefficient of friction tells us, it's an assigned value. So it's almost like a constant, okay? And it's a constant that's assigned depending on the surfaces between, or the surfaces that are interacting with each other. So you see rubber on dry concrete has a coefficient of static friction of 0.8, but a coefficient of kinetic friction of 0.65. So our static friction coefficient should always be larger than our kinetic. Okay, and coefficients depend on the two surfaces that are interacting. They don't depend on the weight. They don't depend on the mass of the object or anything like that, the speed, anything like that. All we're looking at for the coefficients is the two surfaces that are interacting. Okay? Any questions so far on our types of friction? Okay, let's do some problems. Okay, so I'm going to walk you through every step that it takes for these problems, but our overall goal to keep in mind here is that we want to find the horizontal acceleration of this sled. Okay, so go ahead and get this problem written down so that you can see where we're working through here. So these are all the steps that we're going to end up going through, but just know that our overall goal here is to find the horizontal acceleration. So we're going to work through each of these steps, but overall we want to find out A. Okay, so I'm going to get rid of them here pretty soon so that we can see the steps that it takes to go through and I have some room to write them. But our overall goal here is to find horizontal acceleration. Okay. All right, so let's draw our free body diagram here. How many forces do we have acting? How many do we think? One? Which way? Or what force? All right, let's think about this. This object is resting on the ground, first of all. So that means it has to have gravity, always. And if it's on a surface, what does it have to have? Normal force. Okay, those are two that if we're on a surface have to be included always, right? And doesn't escape gravity. It's always going to have gravity. Now it says we're pulling this with a force of 75 newtons. So we've got some sort of applied force here, or pulling force, or whatever you want to call it. Okay, and that's equal to 75 newtons. It tells us that our coefficient of friction is 0.01. That means we must have a frictional force. Okay, and in what direction does our frictional force go? Opposite of our motion, so it needs to go on our free body diagram what direction? Left. Okay, so we have 4 forces here acting. Okay. Our overall goal is to find the horizontal acceleration. So let's think about this. First of all, is our object moving vertically at all? As we're pulling this sled, is it accelerating vertically? No. Okay? So we're not going to be concerned with the vertical part just yet, although we're going to need it. Okay? So let's set up our horizontal net force equation, F net in the x direction, because our goal is to find the horizontal acceleration. Okay, for our net force in the horizontal direction, we're going to take rightward forces minus leftward. So we'd say F applied minus our frictional force. Okay. We can start doing some substitutions. What can we always substitute in for an F net? Mass times acceleration. So m times a equals our force applied, which we know is equal to 75, minus our frictional force. What do we know about the equation for frictional force? What is the force of friction equal that we just looked at? Mu times the normal force. Okay, this coefficient of kinetic friction is equal to mu. That's not a force. Okay, coefficient is not a force. It's that little Greek letter that goes into our frictional equation. Okay, so we're going to go ahead and plug in mu times the normal force here. So we're missing a few things. We know our mass is 50 kilograms. We're trying to solve for A. Our applied force is 75. We know mu is 0.10. I'm sorry, 0.01. I did that wrong. 0.01. And we don't know our normal force yet. Okay? Can we solve for the normal force? Yeah. Yeah. Is our object accelerating vertically at all? No, it's not. So that means if we look at our F net in the y direction, we would take our normal force minus our gravitational force. If we know it's not accelerating in the vertical direction, what does F net have to be in the vertical direction? 0. Which means F sub n minus F sub g has to equal 0, which means our force due to gravity equals our normal force. Okay, I would like for this right here to be a little bit quicker response. Okay, if we know it's not accelerating in the vertical direction, we have to know that these two forces are equal to each other. Okay, I wish we would see that a little bit quicker because we've been doing that part since day 1 of chapter 4, right? If it's moving at constant velocity or if it's not accelerating, our net force is 0, which means our upward forces have to equal our downward. Okay, does that make sense? Are we on the same page with that? Okay, so that means to find the normal force, we're going to take mass times gravity. So we need our calculators out if we don't have those yet. So mass times gravity gives us our normal force of 490 newtons. All right, that means I can plug that back in over here for our normal force. 490 goes here. And now we can solve for our acceleration. We'll have 50 times A equals 75 minus 4.9. which means we get a horizontal acceleration equal to, what'd you have? Yeah, good. 1.4 meters per second squared. All right, we're going to take 75 minus 4.9, and then we'll divide out 50 on both sides. Divide 50 over. If you can do this one on your own, I want you to try and do that. Okay, this is extremely similar to the last problem. But I want you to try and do as much of it on your own as you can. So I'm going to work it quietly. So again here, our overall goal is to find the horizontal acceleration. However, this time we've got a little bit more complex system. We don't have just 4 forces. We've got a force being applied at an angle. So this is an instance where, something's sitting on the ground, we're dragging it basically upward at an angle, but it's not accelerating in the vertical direction. It's still sliding on the ground. Okay, so you've got some sort of a box. You're pulling it with the rope, it's still sliding on the ground, except our force is not being applied vertical or horizontal, it's being applied at an angle. Okay, do you remember these types of problems? Hopefully. So here, our free body diagram. We've got gravity always, a normal force. This time our applied force is going in which direction? Right, at an angle. It's not going to the right, it's going upward at an angle. Okay, and our angle that it gives us here is always from the horizontal, so it's always going to be basically north of east. Okay, so 40 degrees sits right here, and we know this has a value of 100 newtons. Okay, and we have one more force. What is it? Friction. Okay, friction is still going to be a horizontal force, right? Friction would not look like that. because we're not pulling it on an incline. We're pulling it on a level surface. So that means friction is not going to come at some crazy angle. It's going to still be surface to surface. Okay? So there's our free body diagram. Our overall goal is to find horizontal acceleration. What's the first thing that we should do when we see an angle here? A force at an angle? Yeah, we break it into components. We find our x and our y component, okay? So if this is an applied force, what am I going to call this side here? Yep, force applied x. And I would call the vertical side force applied y. Because we don't want to work at an angle, we want to work with vertical or horizontal components. We do not want to work with things at an angle. Okay, so let's go ahead and break that down first and solve for F applied x and F applied y. All right, for x, are we going to use sine or cosine? Cosine, good. So we're going to take 100 times cosine of 40. And get 76.6. For applied y, we're going to take 100 times sine of 40. And get 64.3. Okay, do we have any questions about where these numbers are coming from? Why we're using sine, why we're using cosine for this particular example? So we need to get them out if you have them. Okay? Anytime we have a force at an angle, that should be your first step, is to break down that force. Okay? Because now we're done with the 100 newtons. We're done with the 40 degrees. Those don't get plugged into our equation anywhere. Okay? Once we break that into its components, its x and its y, those are the only two values that we use. So these two values will be the only ones we use now. The 100 does not go anywhere in our equation. Ever. Okay? Once we break it down, we're done with it. Okay, so we can go ahead and start looking at our horizontal acceleration here, our horizontal forces. So let's take F net in the x direction. We'll take our rightward forces minus our leftward. So what rightward forces do we have? Yeah, F applied x. And what leftward force do we have? Friction. Good. Okay. So let's go ahead and substitute MA right here equals 76.6 minus our frictional force. What can we substitute for our frictional force?
Mu.
Yep. Mu times what? Normal force. Okay. We know our mass is 30. We're solving for A. We know what mu is, times 0.30. Do we know the normal force yet? We don't know that yet. So that's going to be our next step, is to solve for that normal force. Okay? Now is where it gets a little bit tricky. Are the normal force and the gravitational force going to equal each other in this case? No, they're not. They are not, because that's not the only two vertical forces we have acting. So we have to take another extra step to solve for our normal force. Okay? So now let's look at the net force in the y direction. How many vertical forces do we have acting here? How many of you think 2? Raise your hand. How many of you think 3? Yeah, we have 3 vertical forces. Okay, and they are the normal force, F applied y, and our gravitational force. We have 3 different vertical forces here acting. All right, so that means we need to take normal force plus F applied y, because they're both going in the upward direction, minus F sub g. Okay. Are we on the same page with that equation right there? And we know why we're having to use this equation to solve for the normal force. Yeah? Give me like a nod if you're feeling good about that. Okay? Make sure if you are having questions or you're unsure, you're asking here, okay? So now tell me, what's the acceleration in the vertical direction? 0, right? The box is still sliding on the ground. We're not lifting it off the ground. It's not leaving the ground. It's not accelerating in the vertical direction. So this still equals 0. But this time we've got 3 forces we have to add up to equal 0 instead of just 2. We're solving for our normal force, so we're going to keep that. We know what F applied y is equal to, 64.3. And we know F sub g is mass times gravity, so 30 times 9.8. So that leaves me with 0 equals normal force minus 229.7. And I'll add this to the other side. And that gives me my normal force. So now I take this value and I can plug it into that equation right there. 229.7. Which gives us a horizontal acceleration of 0.256. So as you work through this, is anyone noticing any red flags? You got a negative acceleration. How many of you got the same thing? Does that make sense? No. So what happens, okay, if we're getting a negative acceleration, essentially what we're saying is that we're pulling it, but it's accelerating that direction. Can that happen? Can friction just randomly move things in the opposite direction? No. So take a look at the big picture here. Look at our applied force, 165. Our frictional force is 189. Is our box going to move at all? No. So we don't even need to bother solving for the acceleration once we determine that our frictional force is greater than our applied force. So our acceleration here is 0. It's not a negative. We just say the box won't move, right? Because essentially, by solving for the acceleration and seeing that we have a negative, what we're saying is that we're pulling it this way, but friction is magically making it like slide that way. And that doesn't happen. Okay? So we're not applying a great enough force here to overcome the static friction force. So essentially our acceleration here is 0. Okay? Or we say the box won't move. Okay? So as you're working through this, you have to take a look at that, see those red flags. So how many of you felt that something wasn't right as you were working through the problem? Right? But you just kept going. Right? You've got to look and trust your instincts there to say, okay, something's not right. Either I did something mathematically wrong, or I've got to take a look at that. My friction force is greater than my applied force, which means my object won't move. Right? If I'm not applying a great enough force to overcome friction, it's not going to do anything. Okay? Okay, so instead of them giving our coefficient, we're going to solve for the coefficient this time. So again, you can start to try to work this one on your own. That's great. Otherwise, I'll start working it out in just a second. So this time is our force being pulled at an angle? No, just a horizontal.